Hello, welcome to this video. In this lesson, we will learn how to implement our first control program in a PLC. We will explore its development using different programming languages, with the goal of understanding the various ways in which control logic can be structured within an automated system. The programming language is the way we communicate instructions to the PLC. Through it, we define how the automatic system should act under different process conditions. In other words, it allows us to tell it what to do, when to do it, and how to react in each situation. According to the International Standard IEC 61131-3, there are different standardized programming languages that facilitate the development, understanding, and maintenance of programs in industrial controllers. This standard establishes a textual language, structured text, ST, and two main graphical languages, ladder diagram, LD, and function block diagram, FBD. It also defines a complementary set of graphical and textual elements called sequential function chart, SFC, used to represent the flow or sequence of a process. Thanks to this standardization, programmers can choose the language that best suits each application or even combine several within the same project, maintaining compatibility, clarity, and uniformity in programming. Next, we will develop a very basic example that will allow us to easily understand how to use the programming tools of a PLC. In this case, we will turn a pilot light on and off using two push buttons. It may seem like a simple exercise for a programmable controller, but you will see that from this principle, much more complex and versatile applications can be built. We must take into account the variables and data types we will use for each one. In this example, we will use two variables associated with the PLC's digital inputs, corresponding to the push buttons, and one variable associated with a digital output that will control the pilot light. In later lessons, we will talk in more detail about signal types and how they are physically connected to the PLC. For now, we will focus on implementing the control logic, assuming that the push buttons and pilot light are already connected to the device. We will name the variables start_PB, stop_PB, and pilot_lamp, referring to the start button, the stop button, and the pilot light, respectively. These three variables will be of Boolean type since they can only take two possible states, on or off, true or false. Therefore, the data type assigned to each will be bool. According to their function, the variables associated with the push buttons will be inputs, while the variable corresponding to the pilot light will be an output. In addition, according to their scope, we will define them as global variables, which means they can be used in different blocks within the program. In this example, since it is a very basic case, we will not use other data types or different ways of defining variables. Here we will work only with memory markers, although it is also possible to define data blocks that are very useful in more advanced applications. All this development will be carried out in the TIA Portal programming environment, although the concepts can be applied similarly in other software. As we move forward in this series, we will learn new structures, functions, and tools that will allow us to develop more complete, efficient, and adaptable control programs for different applications. Before continuing with the programming, it is important to consider the physical contact type of the buttons since this directly influences how the contacts or instructions are defined within the control program. In this example, we will assume that the start button has a normally open, NO, contact, while the stop button has a normally closed, NC, contact. With this clear, we will proceed with the implementation of the program. We will start using the ladder diagram, a graphical language that closely resembles traditional electrical control circuits, which makes it easier to understand and interpret intuitively. The cyclic scanning process performed by the PLC can be interpreted as if it were descending rung by rung, executing the program from left to right and from top to bottom. In our example, we will place an open contact associated with the start button, then another open contact linked to the stop button, and finally a coil associated with the pilot light to close the logical circuit. When running this program, you will notice that the contact related to the stop button changes from open to closed without being pressed. This happens due to the physically normally closed NC configuration of the button. If you want a more visual explanation of this behavior, let us know in the comments. Also, when pressing the start button, the pilot will light up only while the button remains pressed. When released, the pilot will turn off. This happens because push buttons generate short-duration signals that are only active while being pressed. If we want the pilot to remain on until the stop button is pressed, we must add a self-holding branch, in parallel with the logical contact of the start variable, using a contact associated with the output coil. This contact keeps the circuit active even after releasing the start button and only deactivates when the stop button is pressed. This scanning process repeats continuously and at high speed, evaluating the state of all variables several times per second, ensuring a fast and accurate system response. We can also see part of the program implemented in TIA Portal. Now we will see the same example using the same variables but implemented in another graphical language, function block diagram. This language is based on function logic. Its foundation comes from Boolean logic, the same used in digital circuits, where each block represents a function, for example, an AND gate, an OR, or a timer. This type of language is very visual and intuitive since it allows building the program simply by connecting blocks that process input and output signals. In our example, we will use a logical function and OR, which form the basis of this type of programming. There is a whole theory and methodology for developing control programs in this language. However, in this case, we will go straight to practice, applying the functions simply to understand how they work. We will use a logical AND function, in which we will place as inputs the variables associated with both push buttons. Remember that the stop button has a normally closed physical contact, therefore, it is unnecessary to apply any negation to the input. The output of this AND function will be associated with the variable of the pilot light. When running the program, we can see that the stop variable appears green, indicating that its state is 1 or true. Simply put, the AND function activates its output only when all its inputs are in a high logic state, that is, 1. In this case, the output remains deactivated because the start button has not been pressed. When pressed, the output activates, but when the button is released, the output deactivates again. So, how can we make the pilot remain on even after releasing the start button? We can use an OR function to combine the start signal with feedback from the output, that is, the variable associated with the pilot light. In this way, when the start button is pressed, the output is activated and remains on, thanks to the feedback, until the stop button is pressed, at which point it deactivates. We can also see how this logic is easily implemented in the TIA Portal programming environment. There are other ways to achieve the same behavior, such as using set and reset blocks, which simplify programming, but for now, the important thing is to understand the fundamentals of this language and how the PLC interprets control logic. Now we will implement our example in another programming language, SCL. The SCL, Structured Control Language, is Siemens' version of the structured text language defined in the IEC 61131-3 standard, which standardizes the programming languages used in programmable logic controllers. This language is based on the structure of high-level languages such as Pascal, so its syntax is closer to conventional computer programming. Unlike the function block diagram, which is based on gate logic and uses a graphical approach. SCL originates from structured programming, allowing control logic to be expressed through textual statements, facilitating the implementation of conditional structures, loops, and complex mathematical operations. For users familiar with this type of language, its use is quite intuitive, since it only takes a few lines of code to achieve the desired behavior. In our example, we can use the if instruction to evaluate the logical state of the push buttons and, based on that, activate or deactivate the variable associated with the pilot light. The instruction evaluates the state of the start button, and if the condition is true, it sets the pilot light variable to 1 or true. Otherwise, if the start button is not detected and the stop button is pressed, then the pilot variable is set to 0 or false. As you can see, a negation has been applied to the stop variable. This is due to the physical contact type of that button, which is normally closed. Although it is possible to implement other strategies in the PLC to avoid the explicit use of NOT, in this case, we will keep it for a better understanding of the logical principle. When running the program with this logic, we observe that the stop variable is true, but when the negation is applied, its value becomes false. Therefore, none of the conditions are met, and the pilot variable remains off. When pressing the start button, the pilot turns on, and even when the button is released, it stays on. This happens because the condition has set the variable to true, and its value remains that way until the opposite condition is met. To turn off the pilot, the stop button must be pressed, at which point the second condition is met, turning off the associated output. This is the most interesting part of logical programming. If we want to make our program more robust, we can add an additional condition to avoid conflicts when both buttons are pressed simultaneously. In this case, we can include an operation within the first condition so that the pilot only turns on if start is pressed and stop is not held down. This ensures that the stop priority prevails over the start command. We can also visualize this implementation directly in TIA Portal, where the applied logic can be clearly seen. Up to this point, we already understand how to implement or program a PLC in the most basic and direct way. Remember that the choice of programming language depends both on the application and on the programmer's skills and preferences. In the next videos, we will explore the latter language, analyze its most commonly used instructions, and continue delving into the other languages available in TIA Portal. So, we still have a lot to learn.